Hi, in this video I'm going to show you how I turn this regular cap into this 3D printed spout cap. As we all know that it's cheaper to buy a chemical in a larger container. This one is 5 liters or 1 gallon, and sometimes you need to divide it into a smaller container. So when you pour it directly from a large container like this, it's going to splat out everywhere, and you're gonna need a very large cone to pour this out. But if you can make your own spout cap, it's going to be a lot easier. This spout cap has a liquid tube and also air inlet, so you can pour it directly into a smaller container without spilling. I didn't use gasket in this one because the container is made from a soft plastic, and you can tight fit with this 3D print, and it will not leak. First, you need to clone this part, the original cap, make a 3D scan and get the information of the thread profiles and also the pitch of the thread. I divide the spout and the thread into two parts so that sometime when I buy the container, they ship with a different thread, so I only need to change the thread profiles and reprint only this part. And the printing materials I recommend to use with this alcohol, IPA or acetone is the PETG. They never have issue with this solvent liquid. So this air tube is very important because when you pour out the liquid from the container, you need to replace that volume with the air. So if you don't have this air tube, when you pour it for a little while, the flow will stop. But if you put the air tube here, so the liquid will keep coming out at a constant rate. I found that for the size of this cap, the cross-section area ratio between the liquid and the air inlet should be about this. The air inlet size is 4 millimeter and the liquid is about 12 millimeters, so it's a 1 to 3. Okay, now I keep pouring, and if I plug the air inlet, the pouring will stop. Plug. So you need to pour it in an angle that it will not flood the air inlet. Okay, there are several ways to retrieve the thread profiles. One is by make a 3D scan of the male thread. This is suitable if you have adapter series, but if you have a Sermoon S1, you can make a 3D scan of the female thread and retrieve the full profile of the thread, which is not doable with the adapters. This will be the easiest way because if you model the cap from a male thread, you need to consider the clearance between the thread that you are going to make and the male thread. Usually I put 0.2 millimeter for the clearance if you are using an FDM printer. But if you model it from the cap, you don't need to put allowance for the clearance. You just trace the profiles and it will fit perfectly on the first try. So you don't have to do a trial error, and you will most likely will have a successful print on the first time. So this will be an advantage if you have a single line laser. So I will start by scanning the male thread. I will use a blank turntable because I can't put a gallon like this. The thread will be too far from the markers. You need to apply the marker directly onto the container. Because we are going to scan for the thread, so we can't put the marker over the thread. and there's some area that you can put the marker, but it's a round shape, so you need to use a 6 mm marker, the small one. This will be suitable for a small area and also the curved surface. It's a round shape, so when you turn it, it's going to lose the visual of the marker on the other side. But for the plastic container like this, I prefer to scan the cap. So if you have a Sermoon S1, it will be easy because the thread on the cap has a higher quality than the thread from the container. So when you turn it, it's going to see just 4 marker here. So you need to put more marker. So if you use 10 mm markers, there wouldn't be enough area to put many. Okay, here's a Laptop Pro. I'll start with the global marker. So we have 21 markers for cloud. I'll use a cross line because it has a larger capture area. Need to scan a bit longer because I set the resolution to 0.15. Okay, it's all done. The bottom of the profile is rougher than the top of the profile, so this information might be inaccurate. It's normal for the 7 line not to be able to completely scan the whole profiles. The scan of the male thread is not perfect for the cross line because of the position of the marker. You can't place the marker on the scanning surface directly. Okay, let's try with the Sermoon S1 in a single line. See if it can make any difference than the Laptop Pro in scanning the thread like this. Okay, I do the same, but this time I use the Sermoon S1. Switch to single line. Okay, now there is no blind spot. Feels it. Okay, this is the result from the Sermoon S1 using a single line to scan for the thread profiles. You can see that it's also scanned the bottom of the profiles. See, the top and the bottom of the profiles also scanned. So when I compare it with the Laptop Pro, the bottom here is not completely scanned. It has a rougher surface. And this is scan data from the S1 scanning the male thread. You can see that it has a better scan quality because I use a single line to scan the male thread. Okay, next step, I will export this 3D scan data as the point cloud in a ASC format, and then I will align this to the XY plane using Cloud Compare. Okay, this is the Cloud Compare. Just drag and drop the ASC files here. And next, I'm going to align it to the XY plane using 3-point alignment tools. And next, I'm going to move it to the origin point. Now, the center of the cap is in a center point. I need to change the color to the bright color like this. Okay, to be able to give you the idea about the clearance between the male and female threads, so I aligned this male thread that I scanned earlier with the female threads. And you can see that it has a very large clearance between male and female threads. And if I measure this clearance, it's gonna be somewhere around 0.6 millimeter. So it's a very large clearance from the stock cap. The female and the male thread, the profile is not symmetry. Okay, let's move to the Autodesk Inventor and modeling. Okay, this is a cross-section view. This is how the spout attached to the cap. Okay, let's start by modeling the cap. I tell you the step I took to model this. First, I crop a thin section of the point cloud on the top here. And if you draw a circle, you find that the cap is not round. There's some part of the cap that is deformed. To adjust the position of the point cloud, you can go to Edit Attach Data, and there's an offset value here, X and Y. You can move this until it's close match to the origin point as possible. Okay, next I create a sketch here. I draw a cross section of the cap by using the point cloud as a reference. I try to get it as close to the circle as possible, and I use 2.4 millimeter for the wall thickness. So if you are new to CAD is a modeling method that use the sketch to create a 3D model. So everything that you see in CAD is created by using a 2D sketch, and then it will use the command like extrude, sweep, loft, and revolve to make it a 3D model. If you can slice your point cloud into a thin layer, then you can create a very accurate sketch that you can use it for making the model. This is through reverse engineering. After I made the sketch, I extruded for 21 millimeters, about the same height as the original cap. Okay, next I create a sketch on the XZ plane, which is this one. And if you look from the side view here, I'm going to create a thread profile. It's not symmetry, that's one. And two, the original profile has a round shape, you can see here, but I'm gonna print this with the FDM printer. I can't print exactly like this, but if you have a resin printer, you can do the round thread profile like this, but with the FDM you can't. So I make it like a trapezoid shape like this. Okay, next to create a thread, one, you need to draw profiles, and two, you need to find the pitch. The pitch is the distance from peak to peak. I do this by using the array command. So I change this number to 0.5, 0.6, 0.7, 0.8, 0.9. Okay, 2.9 could be the pitch of this thread. Most of engineers, they don't use this number, just round up the number to 3. Next, I'm going to use the coil command to coil it, using this as the spinning axis. Okay, this is the coil command. I select this as a sketch profile and select this as the rotating axis. And what you have to input here is the pitch value and number of revolution. So this number of revolution, I just try to change the number, and I end up with the 3.6 revolve, and it will match the original thread profiles here. This thread can turn at 3.6 round. Okay, after the coil command, I need to create a enclose of the cap on the top here. I use the offset value of 5mm, and then I extrude it for 2mm. Okay, next I create a profile here, trapezoid profile, to make a grip for the cap, and then I extrude it and I chamfer it for 1mm. Then I use a circular array for 10 times, and then I make a chamfer on this corner, and then I also make a chamfer for the start and the end of the thread. So now the cap is done. Okay, let's move to the spout. The spout we have two tubes, one for the liquid and one for the air inlet. Okay, next I extrude the profiles for 2mm. Okay, next I create a sketch and the wall by using the projection lines from the first extrusion, and create the first extrusion just above the top of the cap. Next I make a chamfer here to make a liquid flow smoother. I also make a chamfer for the air inlet as well, a smaller one. Okay, next I create a sketch here for the sweep profiles of the liquid tube, just a 2D sketch that I made on the YZ plane. And you can also adjust this angle. This one is about 50 degrees. You can adjust the curvature of the fillet and the length here. To create a sweep, you need two sketches, sweep part and profile sketch, which is this one, and then I compile the sweep command using two sketches, and I also put taper end of the tube is smaller than the starting point by 3 degrees. Okay, this will be the second sweep command. I use the sketch here to cut the hollow profiles of the tube using the same path. Okay, next I'm going to sweep the air inlet, a fillet here first, and then I create a sketch and make a cross-section sketch, and I will use this line for sweeping the air inlet profiles. So I use this cross-section profiles and sweep on this rail that I just made earlier. Okay, let's send this to the slicer. So printing this is quite simple. I'll leave the download link in the description in the case that you have the same container as I do. And next I'm going to split the object into two parts and turn this side. You can print this without any support. Okay, it will take about 1 hour to print this. Thank you guys for watching. See you in the next video.